All right, here we are. I'm going to move the camera to point at the paper as usual, and I'll take your first question. Let me pin this and you can tell me if it's
Yeah,
in
crystal
focus.
clear.
Great. Welcome to office hours.
Yep.
What's your first question?
It's on the special homework actually, number 6 specifically.
All right, let me take a look. I'll share the screen. So number 6, huh?
Always like starting with the hardest problems.
So it's one of these interval notation problems.
Yeah.
Okay, were you able to find each of the CJs for J equals 0 to 3?
And not yet. Actually, I want to start with number
Well, were you,
6A.
uh-huh. Well, let me just ask you this. Were you able to do 5 and 4?
So far, I started with 1. Yeah.
I'm sorry,
Oh, I did 1.
you did
But
1.
yeah. Like I
Uh,
wanted to do 6 so I can like see if
Okay,
I'm good at it or not.
all right. Well, let's just take a look at it. The first thing is look at what you're asked to find. You're asked to find some unions and some intersections. The first union is from j equals 0 to 3, so that means you want to at least look at C0, C1, C2, and C3, so you can get an idea of what the union of those four intervals is, and then to see what the intersection is. So I'm going to write down the definition for CJ. So C sub j is soft bracket j, comma, j plus 1 square bracket.
Mhm.
And I should have told you, well, of course, we know the j's are always integers, right? So
Yes.
uh, we're going to look at C1, C0, C1, C2, and C3 because we're asked to find the union and the intersection of those, okay?
Mhm.
So let's find C0. So that means J is 0. All right.
Mhm.
So what do we put here? We're just going to put a 0 in everywhere we see a J.
Yeah.
So what goes here?
Be 0 and then 1.
Comma.
Okay.
Yep. And 1. And then square bracket. These brackets and parentheses matter. Remember, soft parentheses means we're not including the 0. But the square bracket next to the 1 means we are including the 1. Okay?
Okay.
And there's an example very similar to this in the class notes. It's just that the soft bracket and the square bracket are in the other order. So what is
Okay.
C1 going to be? You tell me what to write.
Well, since J is now 1, it would be,
So J is now 1.
yeah, it would be 1 and 2.
Well, tell me about the delimiters. What am I going to put outside?
Oh, I'm going to put a soft bracket first, and then the 1, and comma 2, and end with a hard bracket.
Good. Great. Now we'll move to J equals 2.
Okay, since J equals 2, it's going to be soft bracket 2, and comma 3, and hard bracket.
Good. is J equals 3.
So we're going to be soft bracket 3, comma, then 4, hard bracket.
Good. So if we take a look and draw a picture, which is what's recommended, let's just start a picture here. Here's 0. Here's 1. Here's 2. Here's 3. And here's 4. Do you see why I started at 0 and ended at 4?
Yes.
So C0 does not include 0, but it does include the 1. So this is C0. All these numbers in here, including the 1, but not including the 0. Do you see that?
Yeah.
And C1 picks up right after the 1. It doesn't include the 1, but it's as close to 1 as you want. And it goes to 2, and it does include the 2, and it's everything in between. So there's C1. C2 doesn't include the 2, but it abuts, the 2. It's right next to it. And then there's the 3 that we do include. And it's everything in between 2 and 3, including the 3, but not including the 2. And then finally, C3 does not include 3, does include 4, and all the real numbers in between. These are infinite sets. All of these sets are infinite sets. Okay?
Okay.
So, part A, we're asked to find the union from J equals 0 to 3 of the C sub J, right?
Yes.
So that means we want to find C0 union C1 union C2 union C3, right?
Mm-hmm.
So it means we want soft bracket 0 to 1 square bracket union, soft bracket 1 to 2 square bracket union, soft bracket 2 to 3 square bracket union, soft bracket 3 to 4 square bracket. So we need to figure out the union of these sets, but we can see a picture of them. So the X real numbers that are in this union are in either C0 or C1 or C2 or C3, or could be, if there's overlap, an X could be in several of these.
No.
Is there any overlap between these sets?
C0 and C1.
Do they overlap at 1? Is that what you think?
Yeah. Oh wait, no, they don't because the hard bracket at the end.
The hard bracket means the 1 is in C0, but the soft bracket means the 1 is not in C1. So the only place they could have an element in common would be at 1, but 1 is not an element of C1 because C1 does not include 1. So
Okay.
these don't share any elements in common, but their union is any X that's in here or in here or in here or in here. So what do you think that union will be? Where would it start?
Um, I think it would start at,
We read from left to right.
I think it would start at 0.
Uh-huh. Should we include the 0? What kind of delimiter should we put here? Soft bracket or square bracket?
Soft bracket.
What?
It would be soft bracket, right?
That's right. It's soft because we're not
Okay.
including the 0 because it's not an element of C0, is it?
Yeah.
But C0 starts with any, all these real numbers that are real close to 0 are in here right after 0. All right, how
Okay.
far does it go if we're looking at anything in C0 or C1 or C2 or C3?
It would go. only one still because of the hard bracket is C1. I mean C0. My fault.
Do you see that we're going to take any x's that are in C0 or in C1 or in C2? This is the OR operator.
Oh,
Or
okay.
in C3. That's what the union means. It's our OR operator. So any x that's in any of these gets to be in the union.
Okay.
So how far should we go?
We go up to 4.
And do we include the 4
Yeah,
with a square bracket?
it was great. Okay. Okay, I think I'm getting it now. Okay.
All right, let's look. And the class notes are really good because we did a bunch of these. Okay.
Yeah.
Uh,
Sorry, I had a
okay.
quick question. And it's a hard bracket because that's the end of that exact union before it unions with the rest more so.
Well, it's a square bracket because that's the way the set was defined.
Gotcha. So that's how all the sets would be.
Yeah, the sets are all defined to not include the left
The left.
boundary, but
Okay.
they do include the right boundary. The square bracket means we include this number on the right. The soft bracket means we get as close as we want to this number, but we never actually reach it. Like we get as
Okay.
close to zero as we want, but we aren't actually going to include zero.
Okay. I'm writing that down.
So now the next question is to take the intersection from j equals 0 to 3 of the C sub j's, and that's our AND operator. So we're looking for elements that are in C0 and in C1 and in C2 and in C3. So are there any x's that are in C0 and in C1?
C1. Yes.
What elements, what real numbers are in both C0 and in C1?
1.
1 is an element of C0, but this soft bracket
Oh,
says 1 is not an element of C1. So are there any real numbers that are in both C0 and in C1?
no.
No. Are there any real numbers that are in C0 and in C1 and in C2? So that's even a harder
No.
question. No, because there weren't even any in both C0 and C1. And there certainly aren't any X's in C0 and in C3 and in C1 and in C2, right? Because none of these sets have any elements in common with any of the other sets. So intersection is the empty set
Okay.
because there are no real numbers that are in all 4 of those. The next question is, well, what if we just play this union game starting at j equals 0, but keep going forever? So instead of stopping at 3, we're just going to keep going forever. So there'll be some more sets and some more sets. Just keeps on going forever. So it's 0, 1 square bracket, union, 1, 2 square bracket, union, 2, 3 square bracket, union. Just keep on going forever. Well, what's that going to be?
It's going to be unlimited.
It's going to be unbounded to the right.
Yeah.
But what about on the left? What's the right? It starts at C0. So
Uh-huh.
there is a lower bound, but you're right, it's unlimited or unbounded to the right. So how would we express this set?
Would we say, would we use the same answer we used in B? Or is no elements?
Oh no, there are lots of elements because this union includes this union, plus it keeps on going and just never ends. We just keep adding more sets unioning forever.
Oh wait, no, you would put the, I think you would put like soft bracket zero
Yeah.
and then unlimited and hard bracket.
And well, how do we write the unlimited?
I use the unlimited symbol
The infinity symbol.
or the infinity symbol. Yeah.
And we don't ever use a hard bracket with infinity because it's not a number. It's
Okay.
not a number that we can say we're including. It's a concept. It's an idea of this going on forever. So you never put a square bracket around an infinity or a negative infinity. Never. We always use
Okay.
soft brackets because those aren't numbers that give us an endpoint. They basically are concepts saying there is no ending to that direction, in that direction.
Okay.
And then the next question was the intersection from j equals 0 to infinity of the C sub j's. Well, we already found that there weren't any elements in the intersection from 0 to 3, right? There is no x that's in all four of those.
Mhm.
Adding more to the intersection doesn't help our cause as far as finding elements. If we couldn't even find any elements that the first two sets shared, C0 intersects C1, they didn't even have anything in common, then is it going to help us to keep intersecting with more of these sets in terms of finding, you know, some X that's going to somehow now magically be in C0 and in C1 and in C2 and in C3 and in C4 and in all the rest of them? Will there be any X's that are in all of those? See, that's our AND operator. If there's not an X that's even in C0 and in C1, then there certainly isn't an X that's in C0 and C1 and C2. And that means there's certainly not an X that's in C0 and C1 and C2 and C3. And there's still nothing in C1 and in C2 and in C3 and in C0 and in C1 and in C2 and in C3 and in C4. See what I mean? Like just intersecting with more sets just makes the problem worse if your goal is to find elements.
Yeah.
And I believe the last question was about, is this collection C0, C1, C2, C3 a partition of any set? But I think you need to work your WebAssign. Did you work your WebAssign about
Yeah.
partitions? And did you review the definition of partition?
Ooh, I did, but I can't call off the top of my head.
Well, you should have your notes next to you. Do you have your notes?
Yes.
Well, I suggest that you
Did I
work.
answer it?
Yeah.
Sure.
I think I remember reading about it saying how it's like breaking it down into like smaller like
Subsets,
something with sets and breaking them down into like smaller manageable parts or something.
smaller subsets.
Smaller
Yes.
subsets. Okay.
Mm-hmm. Well, is there any set that C0, the collection C0, C1, C2, C3 breaks up into smaller subsets? Let's review the definition of partition. Technically, a partition could just be the whole set, but it's not very interesting. A set A having subsets A1, A2, up to A sub K. Let me just say, given a set A, let me rewrite this. I'm writing on the fly here. Let me do it better. Given a set A and subsets A1, A2, A sub K of A, we say the collection A1, A2, to A sub K is a partition of A if three things happen. One, A sub I is not the empty set for each I equal 1, 2, up to K. So none of these A sub I's is going to be the empty set. 2, A sub I intersect A sub J is the empty set whenever I is not equal to J. That means that they're pairwise disjoint. It means if you take any two of these sets in the collection, like if you take A1 and A2, because I isn't equal to J, 1 is not equal to 2. If you intersect A1 with A2, they'll have nothing in common. If you intersect A1 with A3, I is 1 and J would be 3. A1 intersect A3 will be empty. They should have nothing in common. A2 intersect A3 should have no elements. A1 intersect AK should have no elements in common. A2 intersect AK. If you take any two of these sets, two at a time, and you intersect them, as long as you're taking two different sets, that's what this is telling us. When we say I is not equal to J, we're just saying, hey, we're making sure we're taking two different sets from the collection and we're intersecting them. We should not find any elements in their intersection. So intuitively, that means there is no element from set A that appears in more than one of these sets. And the last property says each element of A does appear in one of these sets. In other words, if we take the union from I equals 1 to K of these A sub I, so if we union up all of these, then we do get all of A back. In other words, if you want to try to get an intuition about a partition, the best intuition is each element of the big set A appears in exactly one of the subsets A1, A2, A sub K in the partitioning collection. So let's look at an example. Let's say A is the set that contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's a pretty big A. We're going to try to build a partition. We're going to let A1 be the evens, 2, 4, 6, 8, and 10. we're going to let A2 be 1, 3, and 5. And we'll let A3 be the set containing 7 and 9. Is the collection A1, A2, A3, is that collection of subsets a partition of A? In other words, does each element of A appear in exactly one of these subsets? And these subsets don't share anything in common with any of the other subsets.
Yes.
That's right. Yes. You know, A1 is not empty, A2 is not empty, and A3 is not empty. That's property 1. Property 2, A1 intersect A2, well, there aren't any elements in common, so that is empty. A1 intersect A3, so when we look at A1 and we look at A3, they don't have anything in common. And A2 intersect A3 is empty. So we do have pairwise disjointness. And then 3, if we take the union from I equals 1 to 3 of these A sub i's, in other words, if we look at A1, union A2, union A3, do we get all of A back? Is every element in A in at least one of these? Yes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when we union those together, we do get all of A. But none of these have any overlap with the others, so they're pairwise disjoint, and none of these is empty. So it is a partition. So now let's go back and look at this collection of sets. It's not, these aren't finite sets. See, these are finite sets. It's a little easier with finite sets, but we can still think along these same lines. When we took the union from j equals 0 to 3, we said, okay, we don't include 0, but we get all the real numbers to the right of 0 up to and including 4. Do you agree?
Yes.
That was the union. Well, since the union of these has to be the whole set, the only possible candidate for the set A that these subsets partition would be this set from 0 to square bracket 4. Do you see how these 4 sets break up soft bracket 0 to 4 square bracket into subsets, and these don't overlap with each other at all, but every element in this set that we could call A does land in one of these?
Yes.
So is the collection a partition of any set? If
Yes.
so, what set? So what set does it partition?
It would be the first one in A.
That's right. It's a partition of that. But things can get really interesting. For example, what if we let b sub k equals square bracket k minus 1 to k, for k equals 1, 2, 3, keep on going. A. Find B1, B2, B3, B4, and B5. B. Find the union from I equals 1 to 5 of the B, K. K, I'm using K. K equals 1 to 5 of the B sub K. C, find the intersection from K equals 1 to 5 of the B sub K. D, are the B sub K for K equal 1, 2, 3, 4, 5, a pairwise disjoint collection? Does the collection B1, B2, B3, B4, B5 partition any set? If so, what set? All right, so let's take a look. Is it still in focus?
It's focused X. We'll see it.
So what is B1?
B1, that would be K minus 1, so that would be 0. Hard bracket 0 and then 1.
Good. What's B2?
B2 would be okay.
What's 2 minus 1?
Okay.
So easy, it's hard.
Yeah. So it
Right?
would be, yeah. So it would be 1 and then 1 and then
It's
2 hard
B2.
bracket.
Yeah,
Yeah,
good.
B2. Yeah.
How about B3?
B3 would be hard bracket 2 and then 3 hard bracket.
Good. B4, you got this.
It would be hard bracket 3.
Uh,
I mean, hard
yeah,
bracket.
yeah, you're right. 3, yeah.
Okay. And then 4 hard bracket.
And then B5.
It would be hard bracket 4 and then 5 hard bracket.
All right, we just fit them in there. All right, so we could draw a picture of these. You know, it never hurts to draw a picture. So it's B1 starts at 0 and it includes 0 and it goes to 1 and it includes 1. So that's B1. B2 starts at 1, so it shares 1 and goes to 2, 3, 4, 5. So B2 starts at 1, includes the 1, goes to 2, includes the 2, right? Because it's square brackets on both ends. B3 starts at 2, ends at 3, right? Everything in between, bunch of numbers in there, infinitely many, and it includes its endpoints. B4 starts at 3, ends at 4, includes the endpoints and everything in between. And then B5 starts at 4, ends at 5, includes the endpoints and has everything in between. Okay, so it's a slightly different picture because see that we got square brackets all over the place.
Yeah.
So what is the union?
I think would be 0, 1, union 1, 2, union 2, 3, union 3, 4, then union 4, 5.
So what does that union become at the end of the day? Let's write it
It would
using
be,
interval notation.
I think it would be hard bracket 0 and then 5 hard bracket.
Nicely done. Now we're going to try to intersect all of those. So we're looking for any x's that are in all of these. They are in B B1 and in B2 and in B3 and in B4 and in B5. Are there any X's that are in this set and in this set and in this set and in this set and in that set?
I would say no, due to the square brackets on all of the sets. I could be wrong there.
The answer is no, but we do have to look at the square brackets, when we're at least when we're looking at this intersect that, B1 intersect B2, they do share the one in common, right?
Yes,
But the one that's in these two isn't in this or that. So even though these two share the number one, the other three don't have one. So one is out. And then when you do the same thing for the two, yeah, the B2 and B3 share the two, but B4 doesn't have the two, and B5 doesn't, and B1 doesn't. So the two isn't in the intersection of all of these. There is no real number that is in the intersection of all five of these.
yes.
But then when we say, okay, are these B sub k's for k equal 1, 2, 3, 4, 5 a pairwise disjoint collection? In other words, if we look at any two of these B sub k's, like these two, or these two, or these two, or these two, or these two, and intersect these two, intersect these two, intersect these two, will we always get an empty intersection? No matter what two we pick? That's what pairwise disjoint means. A pairwise disjoint means if you take a pair of the sets, so like take these two, and you intersect them, they got nothing in common. But you have to be able to say that that holds no matter which two you pick. Will we always have nothing in common, no matter which two we pick? Or does there exist a pair that when we intersect that pair together, we do find some elements, or at least an element?
I would say yes. I think it would be a partition because we do have at least one set like in common, such as 0, 1, and 1 and 2.
That would violate the definition of partition because the element, do you see that the element one is in B1 and it's also in B2?
Yes,
So B1 intersect B2 is not empty, is it?
no.
They share an element. They share that endpoint element. Observe B1 intersect B2, which is 0 to 1 square bracket intersect square bracket 1 to 2. There is something in that intersection, namely just the number 1, the singleton set with 1 in it. And that is not empty. For it to be a pairwise disjoint collection, you have to be able to pick any two at all and never get anything in common. But you see, B0 and B2 have one in common. B2 and B3 have two in common. B3 and B4 have three in common, and B4 and B5 have four in common. But it would be enough if only two of these had something in common, because that's enough to break pairwise disjointness.
Okay.
Does that make
Okay.
sense?
Yes, absolutely.
So, based on the answer to D, could this collection be a partition of any set?
No.
No, because these are not pairwise disjoint. Even though if you take the intersection of all of them, yeah, there's nothing in all of them, but there are two at a time that do share elements. So these are not pairwise disjoint sets.
Okay.
Does this help?
Yeah, absolutely. Actually, yeah.
Well, let me give you one more example. Do you mind?
Oh, yeah, sure. Thank you. Yes.
Because I want to thoroughly explore this interesting question with you. Let's let d sub I equal I to I plus 1 soft bracket. And this is for I equals 1, 2, 3, and 4. Find di for I equals 1, 2, 3, 4. And then we're going to find the union from I equals 1 to 4 of the d sub i's. Then we're going to find the intersection from I equals 1 to 4 of the d sub i's. And then we're going to ask, are these pairwise disjoint? You know, the collection D1, D2, D3, D4. And then does the collection D1, D2, D3, D4 partition any continuous real interval on the real line? And continuous just means no breaks. All right. So what is D1?
D1 would be soft bracket 1, comma 2. Soft bracket.
What's D2? You're getting to be an expert here.
Okay, that would be soft bracket 2, comma 3. Soft bracket.
Beautiful. D3.
That would be soft bracket 3, comma 4. Soft bracket.
D4.
Soft bracket 4, comma 5. Soft bracket.
Great. Now let's take the union. Now we should probably draw a picture because this is a little different from what we've seen before. It's not hard, but it's different. All right, so D1 doesn't include the 1 and doesn't include the 2, but it includes everything in between. It's an infinite number of real numbers. You with me?
Yes.
D2 does not include the 2, does not include the 3, but everything in between. I should have started it at 0, but that's okay. It doesn't really matter. You still get the point here. All right, does that look like a decent picture?
Yeah.
And if we were drawing in high school, there would be open holes here, right? Those are all open holes.
Yeah. I do have a
So,
question.
yeah,
Like, what changes now that we have two soft brackets?
it means that, well, let me ask you a couple of questions and you can probably answer your own question yourself. Is
Okay.
1 an element of any of these?
Yes.
Which one?
The D1.
Well, wait a minute. This is a soft bracket. And that means we're not including the endpoint.
Oh, okay.
So I'll ask you the question again. Is
Okay.
the number 1 an element of any of these?
I would say no.
I would agree. Is 2 an element of any of these?
No,
That's right, because it's not in D1, it's not in D2, and it sure isn't in D3 or D4. What
no,
about 3?
no,
What about 4?
no,
What about 5?
neither.
That's right. So this looks a lot like what we had before, except the integers, instead of having overlap at the integers, where the integers are actually in the 2 adjacent sets, right? That's why they weren't pairwise disjoint, because they overlapped at the integers, right?
Mhm.
Instead of having that situation, none of these sets has any of the integers in it,
Uh,
as opposed
okay.
to the situation where we played with what's called a clopen set, open on one side, closed on the other, where one of the sets would get the integer, but the other one wouldn't. C1 gets this integer, but C2 didn't, right? So these are continuous, there's no gaps, but only one of each of these got an integer. So they were pairwise disjoint because there was a soft bracket next to the square bracket, you see? So we've got that situation that did give us a partition because there were no breaks or gaps, but there was no overlap. We had this situation, there were no breaks or gaps, but we had an overlap, and that blew the pairwise disjointness property, so we can't have a partition.
Mhm.
Here, we got gaps. So when we take the union, what do you think the union is? And just tell me with your own words, and we can worry about the notation in a minute, and I'll show you how to write the notation. But just intuitively, if we say we want to write the set that is anything in D1 or in D2 or in D3 or in D4, what do you think you would like to say is in that union? Well, let me ask you
Mm,
this. Do you want 1/2 to be in there?
yeah,
Sure. Do you want 3.1 to be in there?
yes,
Great. Do you want 2.5 to be in there? 2 2/3, 2 4/5, 2 6/7, 2 99 100ths to be in there?
yeah, all that.
All that. So, what do we not want to say is in the union?
Any real numbers like one or two or
Or
three, four, five.
that's right, the integers. So if we take the interval, we're not zero. I should have started at 0 to be consistent. Oh well. We start at 1, but we're not including 1, right? Soft bracket 1. And we go all the way to 5 and soft bracket it. This does not include the 1 or the 5, but it does have the 2 and the 3 and the 4 in there, right? But we don't
Yeah,
really want them because they're not in there. So we
yeah.
subtract away the 2, the 3, and the 4.
Oh,
Ah, subtraction comes in handy.
yeah.
Or
Okay,
you
I
could
see it now.
actually, you could say 1, 5, you can subtract all of Z. It's because it doesn't matter if we subtract more than is actually in there. Remember,
Yeah.
like 25, we could subtract it away, but it was never in there in the first place, so nothing happens.
Mhm.
Now, what about the intersection? Are there any real numbers that are in 1 soft bracket, 2 soft bracket, and in 2, 3 soft bracket on both ends, and in 3, 4 soft bracket on both ends, and in 4, 5 soft bracket on both ends? Are there any real numbers in this intersection? Is there any real number that is in here and in here and in here and in here?
Let's say no.
You would be right. So that's the empty set. There are no elements that are shared. And in fact, are these pairwise disjoint? If we take any 2 of these, this one and this one, even though they're next to each other, look, they don't share anything. This one and this one, 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 no problem. They're pretty far apart, right?
Yes.
The problems might be if we intersect these that are adjacent to each other. But do they have anything in common?
Mhm.
Do they?
All right. They both have two, actually.
What?
So-
What? What? What does this
Yes, it is.
soft parentheses mean? It means
That's
we're
my,
not including the two. We're
yeah, my mistake.
see what I mean? Like
Yeah.
these two sets, they sneak up on two from one side and they sneak up on two from the other side, but neither one of them actually hits the two.
Mhm.
So, yeah, if these were both square brackets, they would share the two, but neither one of these even has the two, so they can't share the two.
Yeah. Okay.
So
Well, that's my
so
fault.
no, no, you're fine. You have to just think it through once or twice, and then it starts to become easier. That's why I wanted to show you this example, because it's really different.
Okay.
Yes, D1 intersect D2 is empty. D1 intersect D3 is empty. D1 intersect D4 is empty. D2 intersect D3 is empty. D2 intersect D4 is empty. D3 intersect D4 is empty. If you take any two of them, it's four, there are four of them. Four choose two, by the way, is six. So of these four sets, I'm choosing two at a time. These two, these two, these two, these two, these two, these two. Four choose two is six. So there's six intersections to check because four choose two is six. And they're all empty. They don't share anything. So yes. Now, does this collection partition any continuous real interval? Nope, because the integers are missing
Okay.
in the middle. In the middle are missing. So they can't so the union, from I equals 1 to 4 of these D sub I is not equal to the continuous interval from 0 to 5 because these three numbers aren't in there. So not every real number in this interval is in the union. So now if I didn't require it to be a continuous real interval with no breaks, then we could say that, yeah, these four do partition this set, but we generally want to deal with continuous intervals if we're going to play partition games, but not always, not always. But this worked out nicely to partition because there was no overlap, but we did get the integers in at least, in exactly one of each of these. So that's why it worked to be a partition. Every real number was in there, including the integers, but no real number was in more than one of these between 0 and 4. So I'll leave you with a challenge.
Yeah, that was a good challenge, Tom. I learned a lot.
I'm so glad. You're like a sponge. Challenge. Find an infinite collection of intervals that will partition this real interval. So our set A is going to be square bracket 0 to infinity. Define these subsets using indexed notation like we have seen in examples 1, 2, and 3 tonight. Okay. So just to review, it was actually example. It was actually number 6, but I'll just call it example 1.
Right.
So this was the first one we did.
Mhm.
Then the second one was when we had overlap at the integers. The third one was when we had holes at the integers. And for all of those, we defined the sets, using indexing notation like this. Where, so you would, so your A sub I would equal something. But you want the union from I equals whatever you want to start at to infinity of your A sub i's to equal your set A that I'm given to you, which is all the non-negative reals.
See if I can do that. Yeah.
Have
Might be a
fun.
bit tricky though.
Check out the class notes because we looked at an example that'll help you. And of course, we already know that if you have both soft brackets, you're going to be losing all of the integers. And we already know if you have both square brackets, you're going to have too much overlap because you can't have this overlap between any of them. But we did see the Clopin set work, but it had soft bracket here. Look in the class notes. We want a square bracket on one end. All right. Jessica, do you have any other questions?
No, not for tonight.
Did you learn something?
Yeah.
That's
The
great.
explanations did help, yeah.
That's great. And thank you so much for being here. And Alpha, thank you for a fantastic introduction to partitions. Because of you, we have a really nice recording.
Yep.
All right. I'll see y'all later.
Okay, thank you. Have a good night.
You too.
Yeah. Have a good night, Professor.
Good night.
Mhm.